Hi, welcome back. So we did the traction boundary conditions last time. Now we are going to take a look and we are going to look at what happens inside the body. So just to give you a quick overview of what the story was. If you remember, we had our continuum potato and we looked at the skin. The skin of the potato has four pieces. There's a place where non-zero force tractions, forces per unit area are given. That's up here. Then there's a place where displacements are specified, that's down here, and there's a place where normal displacements and tangential tractions are specified, and then there is a space where nothing is specified actually, but in reality nothing means it's free. That free boundary means tractions are zero. So that's the four pieces, and we wrote down what are the conditions on the four sides. Okay, and we saw an example. Now what happens inside the potato? So here is the inside of the potato, here is the boundary, here is the inside, and what we want to say is on the inside Sijkl must be specified. This is the compliance matrix. And what else must be specified on the inside? We need to know body force, F body force must be specified. Now, there's always a confusion between contact forces and body forces. Body forces are due to the external effects of non-contacting bodies. This is force due to magic. I told you, no, this is called for action at a distance. And for us, the only types of body forces are gravity and electrostatics, magnetostatics. Notice how I said that. I did not say electromagnetism. If you have combined effects, then our whole continuum thing we have to redo. There's huge headaches. So only these three things. If it is not one of these things, it's not body force. Okay. So let us be very clear. So this has to be specified. Is there any gravity effect? Is there any electrostatic effect? Is there any magnetostatic effect? Those are the three things that must be specified. So usually people will put arrows like this and say B or F. Okay, so that must be specified. So those two things must be specified, and things depend upon whether this Sijkl, that is a stiffness matrix, is a continuous function of X or not. Is Sijkl a continuous function or not? If it is not a continuous function, like what happens in a composite material, you will get S1Ijkl here, S2Ijkl here, and this is called an interface. Okay, so those are the things that have to be specified: body force and Sijkl. And what do we want? We are interested in finding the stress on inside the potato and on its skin as well as and U. So we are interested in finding stresses and displacements inside the potato and on its skin. the stresses. So now we come to, okay, how do we find it? So let us make some definition. So in order for us to make our life easier, we are going to make our definitions for only boundary conditions type 1 traction specified, type 2 displacement specified, or type 4, which is I have stress free, so, or traction free. I should not say call it stress free. So I have one region here. So this is type 1, this is type 3, sorry, this is type 4, this is type 3, sorry, type 2, no type 3. Because we'll have some problems with type 3 for now, so let us not worry about it. When we come to it, we'll cross that bridge when we come to it. Okay, so a stress field is said to be statically admissible if it satisfies the equations of equilibrium in every part of the body. So what do I mean by that? If I take any portion, let's say I take a portion like that. Okay, we are not done yet. So this is if A, this is part A, that means i.e. so this is the part. So let us be very careful. In every part of the body. So in this part of the body, integral of traction on that part dA plus integral body force dV must be equal to 0 for every part. This is total contact force. This is total body force. And we know that instead of doing this, the way we calculate T is sigma times N. So we have integral sigma times N dA plus integral B dV must be equal to 0 for every part. That's item number 1. And item number 2, on those parts, surfaces where traction is specified, they must agree. That means sigma times N must be equal to T on partial omega 1 and must be equal to 0 on partial omega 3. What do I mean by that? Look, if I can find a stress that satisfies equations of equilibrium inside the potato and it satisfies this on this surface of the potato and on this surface, it does not have to satisfy anything here because anyway I didn't know what the stress was, so I didn't care. But wherever I know the stress, it has to satisfy that. Wherever I don't know the stress, it has to satisfy equilibrium equation. If that is the case, it's called a statically admissible stress field. So intuitively, if I know the stress or its component or some components, it should agree. If I know Else, if I don't know, it should at least satisfy equilibrium. And in most cases, the way we check that is not doing this. The way we check that is not doing this, but by looking at, we won't do this, but instead we check sigma ij comma j plus bi equal to 0. Is this true or not? And then of course I want to check sigma ij equal to sigma ji. That's what I'm really going to check. So I'm going to rewrite this as saying sigma ij comma j plus bi must be equal to 0. Sigma ij equal to sigma ji and sigma times n equal to t on partial omega 1 equal to 0 on partial omega 3, sorry, or partial omega 4 can be anything on partial omega 2. So remember, 1 is traction specified, 4 is traction free, 3 is displacement specified. So at places where displacement is specified can be anything, we don't care because we don't know. Try places where it's traction free, better match. Places where tractions are known, it had better match, and every other place it has to satisfy equations of equilibrium. That's called a statically admissible stress state. So let us look at an example. Our hanging bar, okay, and just gravity is the only body force. B equals rho g in the negative k direction, okay, and we want to see a statically admissible stress field. So I'm going to put sigma zz. So remember, z goes from here and it goes x and y like that. So sigma zz equals rho g times z. All other sigmas are 0. Will this satisfy the equations of equilibrium? Well, let's see. All I have to do is sigma zz comma z equal to 0 plus rho, minus rho g, this all the k direction must be equal to 0. True. All others automatically satisfy because everything else is 0. The other two conditions are automatically satisfied. So it satisfies inside. How about on the boundary? Well, on this boundary you can see the normal direction, n equal to minus I, n equal to plus I, no problem. The only things that matter are n equal to minus k here, and if I substitute z equal to 0 here, the stress is 0 here, so that's true. On this surface I don't care because it's a displacement specified surface. I don't know the traction, so I don't have to meet anything. It seems to satisfy everything that we asked for. Super, so we got that. That's called a statically admissible stress field. It doesn't mean it's a correct stress field. All it means is that at least I managed to satisfy the equations of equilibrium. Thank you.